Welcome to the Explainer. Okay, let's just dive right into this. If you're gearing up for your next physics exam, well, consider this your ultimate study guide. Today, we're going to completely demystify current electricity. And we aren't just going to sit here and memorize formulas. We're actually going to build a structural understanding of how the invisible world of electricity truly works. By the end of this, you're going to see the circuits powering your entire life in a completely new light. So here is our syllabus for today. We're going to build up our knowledge sequentially. We'll start all the way down at the microscopic chaos of atoms, work our way up through resistance and power, figure out how batteries act as our engines, and then finally scale up to mastering complex circuit networks. All right, Section 1, the fundamentals of flow, moving from micro-chaos to macro-control. To really get this, we need to understand the microscopic why before we ever try to calculate the mathematical how. So I want you to ask yourself a basic, yet kind of profound question. What is actually happening inside a simple copper wire? Because, to answer that, we have to look way past the solid metal we can hold in our hands and imagine the invisible, completely chaotic movements of electrons hidden inside.
Notice the stark contrast between these two states of being for electrons. Without an electric field applied, these charge carriers are trapped in a state of pure micro-chaos. They have super high thermal velocity, but they're just bouncing around randomly. That means their net velocity is exactly zero. They're going nowhere fast. But the moment we apply an electric field, bam, we establish macro control. We get a directed flow. And while their actual drift velocity is surprisingly low, that non-zero average means we finally have an electric current.
You can actually see that transformation happening right here. Looking at the blue section, you see that thermal energy and noise. It's a chaotic, zigzagging mess of random thermal motion. But look at what happens as we move into those terracotta-colored pipelines. Applying an electric field creates a directed, highly organized flow. The net movement is suddenly pointing in one clear direction. And that directed current, that's what we call drift velocity.
Let's use a visual metaphor that usually makes this click for a lot of students. The water analogy. We can think of the flow of charge a lot like water. An unsteady flow is like a disastrous, momentary lightning strike. Millions of amperes discharging all at once, just totally chaotic. But steady flow? That's controlled. It's so much like water smoothly navigating a pipe or a riverbed. When we study current electricity, we are studying that controlled, steady, and actually useful movement.
So the absolutely crucial point is this definition right here. If you want to ace your exam, you've got to burn this into your memory. Current, which we represent with the letter I, is simply the mathematical rate of that steady, forward-moving charge. It's the limit, as the change in time approaches zero, of the net charge divided by the time interval. Basically, it's just a measurement of how much charge is crossing a specific area in any given moment.
Okay, moving on to Section 2, Ohm's law and resistance, the rules of flow.
Now that we've established how current flows, we need to examine the forces that push back. Nothing in the universe is perfectly frictionless, right? And electricity is no exception. To understand resistance, think of the pinball electron. Imagine an electron as a little silver ball in a pinball machine. The machine is full of stationary atoms, or ions, acting as the bumpers. When we apply an electric field, it's literally like we're tilting the entire pinball board. The electrons still bounce chaotically off all those ions, but because the board is tilted, they inevitably and slowly drift in one specific direction down the board. That average time between collisions is exactly what determines our resistance. Zooming out from the microscopic pinball machine to the macro scale of a real wire, we find that resistance is strictly governed by physical geometry. Think about it. If you take a wire and double its length, you literally double the potential difference required to push the exact same current through it. Resistance is directly proportional to length. On the flip side, look at the cross-sectional area. If you cut that area in half, making the wire thinner, you cut the current flow in half for the exact same voltage. So resistance is inversely proportional to the area.
This really predictable geometric relationship gives us Ohm's law. But here is a massive trap for physics students. Ohm's law is not some universal law of nature, like gravity. It actually has boundaries. While it assumes a perfectly linear relationship, modern electronics intentionally break this rule all the time to make things, like the computer you're using right now, actually possible.
Take a close look at this comparison. Metals are ohmic conductors. They show this beautiful, linear, proportional, and symmetric relationship on a graph. Double the voltage, you double the current. Super simple. But non-ohmic conductors do not play by those rules. Diodes, for example, are sign-dependent and asymmetric.
If you reverse the voltage, they completely halt the current. And materials like gallium arsenide are even wilder. They're non-unique, meaning the exact same current value can result from multiple different voltage values. So, when you're taking your test, always check if the material you're dealing with is ohmic before you blindly apply that V equals IR formula.
All right, Section 3, Power and Energy Loss, the toll of flow.
As we saw with our pinball analogy, forcing electrons through a resistor full of atoms isn't a free ride. The system exacts a pretty heavy toll. Follow the sequence here. First, the electric field pushes the charge, increasing its kinetic energy. Second, that electron inevitably crashes into a stationary ion in the atomic lattice. The kinetic energy gets transferred right during that collision. And third, that ion absorbs the energy and starts vibrating violently. That vibration radiates outward as heat. We call this ohmic loss. It's exactly why your laptop gets hot. And it's governed by the equation power equals current squared times resistance. Because current is squared, if you want to minimize power loss in, say, long-distance power lines, you have to keep the current as absolutely small as mathematically possible.
Moving to Section 4, Electromotive Force and Batteries, the Engine of Flow.
We know resistance is constantly stealing our energy and turning it into heat. So, to maintain our flow and overcome that persistent resistance, we rely on a power source. We need an engine. Our engine is usually an electrolytic cell, like a standard battery. Inside these cells use chemical exchanges to maintain a permanent potential difference between the positive and negative electrodes. We call this the electromotive force, or EMF. But please, don't let the name trick you on an exam. EMF is not a physical force measured in newtons. It is strictly a potential difference measured in volts when the circuit is open.
Here's another really vital exam distinction that catches people off guard all the time. An ideal cell that you see in intro physics problems provides perfect, constant voltage regardless of the current. But a real cell? The electrolytes inside the battery actually resist the flow of their own current. We call this internal resistance, which you'll see labeled with a lowercase r. As the current increases, the available terminal voltage actually drops. Basically, the battery saps some of its own energy just to function.
And that brings us to Section 5, Complex Circuit Network Rules, governing the grid.
Up to this point, things have been fairly linear. But what happens when we start wiring multiple batteries and dozens of resistors together into these complex, branching webs? The basic rules kind of collapse, and we need a much stronger framework. To solve complex grids, we rely on the universe's most unbreakable conservation laws, codified for circuits as Kirchhoff's rules. First, you have the junction rule, which is just the conservation of charge. Second is the loop rule, which is the conservation of energy. Let's break these down visually.
I absolutely love this topographical metaphor. To intuitively grasp the loop rule, imagine your circuit is a map. The rule states the algebraic sum of changes in potential around any closed loop is exactly 0. Think of the battery as a steep mountain, a big elevation gain. As the current travels along the constant potential wire, it's just walking on a flat plateau. Then it hits a resistor, which acts as an elevation loss. By the time the current completes the loop and returns to the battery, the net elevation change must be 0. You literally always end up exactly back at your starting altitude. Energy is perfectly conserved.
And we can harness these exact rules in really clever arrangements, like the famous Wheatstone Bridge. By arranging 4 resistors in a diamond shape, we can find an unknown resistance with absolute precision. We just tweak the known resistors until the meter in the middle reads exactly 0. We call this the null point condition. At this perfect balance, the cross potentials are equalized, meaning no current flows across the center bridge, and we can easily calculate that 4th mysterious resistor perfectly.
Wow, okay, we've covered an incredible amount of ground today. Let's head into our final section, the final exam review checklist, to make sure all of this actually sticks.
Take a moment to review this study guide summary. Look, the secret to acing physics isn't just mindlessly memorizing the core formulas. It's anchoring those abstract mathematical formulas to tangible visual metaphors. When you see current, I want you to think of that steady water pipe. When you see resistance, picture the pinball machine. When you see power loss, think of the violently vibrating lattice creating heat. And when you tackle Kirchhoff's loop rule, imagine hiking that topographical circuit map. Connecting the math to the visual is what truly locks the knowledge into your brain.
And that wraps up our explainer for today. We've taken the micro chaos of billions of electrons and traced it all the way up to the macro control of complex circuit grids. Electricity is no longer just some invisible magic, right? It's a predictable, structural flow of energy obeying the fundamental laws of the universe. So, the next time you plug in your phone or just flip on a light switch, I want you to ask yourself, how will you look at the hidden energetic networks powering your everyday life differently from now on? Keep studying, stay curious, and you are absolutely going to crush that exam.